Okay, so good morning, and today we study an alternative approach to classical mechanics, and that's called the Hamiltonian approach. And so, before we do that, uh, we will consider, we will first revisit Newton's equations for a particle moving in space under the action of a conservative force. Okay, so F is some minus gradient of some potential. Okay, so the Euler-Lagrange equations of motion. Are just m d square x by dt square equal to minus gradient d of x. Okay, so the features here are second order ODE in time. Okay, so this is what we have, and we put boundary conditions of, we saw that x at 0 and x at some later time t are specified, and we noticed that uniqueness was not always guaranteed. By the above boundary conditions, right? So let's start with uniqueness. Uniqueness is restored if we move to a first order formalism. Okay. That means first order ODE in time. Okay. So we do that in the following way. We define P to be M. Actually, I should write it in a slightly different way. dx by dt is equal to P by M, and dP by dt, what is that equal to? Minus gradient of V. Okay, so now here we give initial conditions at initial time, say t equal to 0. I'm just choosing it to be 0 for simplicity, and in the form of x at 0 and p at 0. Okay, so this is a point in phase space. All this we know, right? I mean, are there any questions and comments so far?
No, sir.
Okay, good. Okay, so, and we know, so also uniqueness is the same as saying that phase trajectories, two distinct phase trajectories don't intersect. We saw all these things, right? Okay, So the question is, can we do something similar? Okay, can we do something similar for a generic Lagrangian system? Okay, so what is it we are given? We are given L of, so let's say the Qi dot, and some time. And Euler-Lagrange equations, of course, is d by dt. Okay. So the answer is kind of interesting. So the answer is as follows. Okay, so so we choose 1 degree of freedom for simplicity. Soon I will generalize it. So in this case, L is a function of then Q dot, and time. Okay, so consider the combination. P Q dot minus L. Okay, we have seen a combination like this before. When did this kind of combination come?
Also, no time dependence.
Yeah, exactly. Okay, so for good point. Okay, so we saw this when there was no explicit time dependence, and we had to identify P with dl by dq dot. Okay, these were the two things that we for which we had seen a combination which looked like this. But at this point, so let's call this thing H. Okay, so we are not going to assume P is equal to dl by dq dot yet. We will just say this thing. So right hand side is a function of P, Q dot, and T. Right? Is that okay? So
Sir, what is P then here?
P is nothing. At this point, nothing. I will eventually we will do something where we'll identify P with dl by dq. Okay, write this at this point.
Okay.
Okay. So now let us do arbitrary variation with respect to, should I put T also into the process? So let's put that in. So when you have a function of 3 variables, you can vary 3 or 4 in this case. You can vary all these guys independently, right? So d of h would be, first we can vary P, that would be dP times Q dot plus P times dQ dot, change in dQ dot. Okay, and then from here we'll get minus dl by dq. This is calculus, right? I'm not doing anything fancy. Minus partial derivative of q dot d of q dot. Okay, plus then the last one would be minus okay. So this is just a change in 4 variables. Okay, let's suppose, and let's just collect, let me do one more thing. Let's collect all the terms together. So first let's collect terms which are proportional to dp. There's just one term, so q dot dp, then dq dot, let connect, p minus dl by dq dot, d of q dot, that is this and this, and now the other terms are just usual, dl by dq minus dl by dt. Nothing deep about this formula. Okay, so what this says is that if you make changes in p, q dot, q and t, you get these terms. That would be the change of dp. But something special happens, special or interesting. If we set p equal to the same combination which we saw before, what happens? Anybody?
Second term goes to 0.
0. So then it looks like dh is a function of three variables only, p, q and t, because these are the only things which remain. Okay, then it's as if h is a function of p, q and t. Okay, so this is what is happening. So this is the reason to go ahead and choose these things. Okay, so this is what we get, and okay, so good. So, but now what does this mean? So let's look at this. So so we have to make sense of this formula being independent of what does p equal to dl by dq dot mean. Okay, what it means is that we use this equation to eliminate all occurrences of q dot in terms of p and q actually. That's what we have to do. Only after we do that, so it's not enough to say p equal to dl by dq dot. If you come back and look at this formula, it still will have q dots going around. Okay, so what you have to do is to, wherever we see the q dots, we see a q dot here, we see the argument as well, we should write q dot. Okay, so we write q dot equal to q dot of some q at p. This is what it means. Okay, so this is the content of choosing p to be dl by dq dot. Okay.
Sir, one more thing. Was the converse true that if we say that p equals to dou L by dou q dot, then L will be independent of time? Was this statement also true?
No.
Okay, sir.
So there we had p as a function. P was written as p was a function of q dot and q. It just said, I mean, the p was just some placeholder. We just called it. We defined it to be generalized momenta. We didn't think of it as an independent variable. We just said that p is that function of q dot and q which you get by taking the partial derivative of L with respect to q. Okay?
Yeah. Okay.
Yeah. So let's now do the left hand side. So we are given that h is a function of only three variables, b and q and t. So that would just say that Okay, so we compare, let's call this equation 1, and let's call this equation 2. Okay. So let's look at this. So equation 1 is just the right hand side of this equation being evaluated infinitesimally. That's what we did. But now O2 is where we are looking at h as only a function of three variables p, q, and t. And now we have to compare them. So we just compare, look at the coefficient of dp. Sorry, I have to keep going back and forth. That is just q dot. Okay, so we get q dot equal to dh by dp. Okay, and then we get this term drops out minus dl by dq equal to dh by dq, and the last one says that I think minus dl by dt equal to dh by dt. Okay, what have I done here? I just compared terms and I get this. Okay, so this is what happens, and so this kind of change of variables. Okay, so it's called the Legendre transform. Okay, so
Sir, are we allowed to compare like this when, dq dot is there in that equation but not there in this one?
it's not there. I mean, it's no longer there in equation 1 after setting.
Okay, so I just have to write it.
So yeah, no. So in 1, impose okay, otherwise we can't compare. Okay, so the Legendre transform, what it did is that we traded q dot but traded for a different variable p. Okay, it's interesting statement that if you do it one more time, you will go back that way. Okay, so it's a two-way. So number of variables are not changing. Okay, so okay, so this is what we get, and okay, so so far we have not used. So we'll come back to this. I just want to spend some time on the Legendre transform. Now I'm just trying to think what I should do. So let's. No, let me do this first. So let's look at the Euler-Lagrange equation. What happens to the Euler-Lagrange equation of motion? Which was d by dt of dl by dq dot was equal to dl by dq, right? So first thing we know, what is dl by becomes? The following. It becomes, so dl by dq dot is, after I do the Legendre transform, it is just d by dt of p equal to dl by dq, but we want to rewrite it as this thing, dh by dq. So use this equation. Okay, so we can combine. So we get these two kind of equations. This is the equation. So we get two first order equations like we wanted. dq by dt was equal to dh by dp. Okay. Again, one more thing which I have done is to use, Q dot is dH by dP, which we have, and this equation is dP by dt is equal to minus dH by dQ. So what we have is two first order in time, of course, the differential equations, ODEs in time. Okay, and there is a new function, the Hamiltonian, okay, is H, which is a function of P, Q, and T. Okay, and these equations have a name. They're called Hamilton's equations. Okay, so we can see that this is exactly what happened with Newton's equations, right? There was d by d for every degree of freedom. We wrote something like this. Okay, so for multiple degrees of freedom, it's very easy to just put qi and pi, but I will do that later. But okay, so is this clear? So what we have gone is from this Euler-Lagrange equation, which is second order in time, to something which is two differential equations which are first order in time. Is this clear? So Euler-Lagrange equations get replaced by Hamilton's equations. Lagrangian becomes the Hamiltonian. So we're going to take a digression now. Digression. What is this Legendre transform? Before that, I'll pause. And is it clear that we have achieved what we set out to do? Hello? Are people
Yes,
there? Or
sir.
Yes, sir.
Yes.
Yes.
Right? We have achieved this without, for Newton's equations, we are able to do it by hand, by readjusting things, etc. But this is exactly that structure. And so simple exercise to work out what it is. So let's do this thing. So the idea here is, we will simplify things a lot more. So if you think about it, in this thing, all we were doing is replacing Q dot with P. So there's only one variable of the, three variables Q, Q dot, and T, which was actually playing an active role. So we'll just focus, let f of x, okay, be a function of a single variable. Okay, and we will do exactly what we did. Let g of p be xp minus f of x. Okay, so this is exactly like if you take x to be q dot, then you will see this thing. Okay, so but we need to and with e equal to df by not partial derivative, ordinary derivative. Okay, so let's draw a graph and try to understand what does this mean. What is this data of p? Okay, so let's draw a graph. Okay, so let's say that x f of x. So we have a function. Okay, so suppose we have a function like this. Okay, so I need some other color, so let's choose blue. Okay, so let's say that we have a point here is x. So we pick here. So f of x is a value of this function. And is blue looking, can you see blue properly?
Yes, sir.
Yes, sir.
Okay, good. Okay.
Yes, sir.
So let's look at what does this say. P is the slope of f at x. Pick some other point. This would be the slope. Pick another point here. This would be the slope. Okay. So what? So if you are giving me P, what you are giving me is a bunch of slopes at every point. And if you know, at least if it is like this, if you know how the slope changes up to some additive constant, in the sense that I can always move this curve up and down, right? The slope will not change, right? If I add a constant to f of x, so let's ignore that constant ambiguity. Then you can see that if I told you how the slope changed at every point, then I should be able to reconstruct f. That's roughly what one has in mind. And so the claim everything about the function f. Okay. By now you will not, nobody asked me this question that once I choose this thing, g of p is not a function of x anymore. So we have forgotten about this thing. So what we are saying is that if you give me p, the value of the slope, you're giving some number g. From that we should be able to reconstruct. F. Okay. So example. So let's do a nice example. So let f of x be equal to some a times x square. A is a constant. Okay. So let's do the Legendre transform first. So P, no partial derivatives here, just ordinary derivative. Okay. So what does this say? That we should invert things. So replace x, where we can trade x for P. So x equal to P by 2a. Okay. So let's do the Legendre transform. So that is g of P equal to Px minus f of x. Okay. And then wherever we see x, we should write it in terms of P. So this will become P. X is P by 2a minus f of x, again, is ax square, right? So it's a into P by 2a whole square, right? So this is equal to, if you look carefully, this is just P square upon 4a. Okay. So the thing is, let's just pick a sign, suppose. So nice feature here is that, so let's plot. Oh, I shouldn't. My f of x was centered at 0, so I should do a better job than this. Okay. And if you plot g now what g will be with respect to p. Okay. So, and we have a mapping, right? So what we have is for every point x in this, I can give you what p is, right? So there's a one-to-one mapping between the slope at x and x. So that's what is happening. But now what we can see here is that both f and g, so the remark which is important is both f and g are, both are minima. Okay, so the key point is that the minimum of this gets mapped to the minimum of g. Okay, if you take a to be negative, then, okay, so more generally, extrema go to extrema. Same kind of extrema. So minima goes to minima, maximum goes to maximum. So convex and convexity, that is positive, convexity is preserved. Okay, why am I saying this? Let us just ask a few things. So what you can do is suppose we have a function f of x, which is not ax squared. Okay, suppose. Is not quadratic in x, okay, but okay, and let's say that we have an extremum, so f prime of x equal to 0 at x equal to x naught. Okay, some minimum or extremum. Okay, so then in the neighborhood of x naught, we can write f of x will be f of x naught plus df by dx at x equal to x naught into x minus x naught plus right. I'm just Taylor expanding it about the extrema. So what is happening here? So let's look at all the terms. Okay, so first thing is this is a constant, so we are not interested. I said that we can shift f of x up and down, so f of x is not interesting from that viewpoint. What about this term?
It's 0, right?
It is 0 because it's an extremum. So you can see that, and also shifting the origin, I mean x naught, we can make it locally the origin. So we will see that at least locally near x naught, f of x, looks like a x minus x, where a is equal to okay. So you can see that the argument that I had goes through. So you can see that the locally at least the statement is true. Okay, globally there might be issues, and so there could be situations where this invertibility that we had. So here we were able to nicely go and back and forth that x and p, if you give me, there's a unique map, right? So suppose you have something which is f of x. So these are all and it will go through if they are like this, single humped unimodal. So it goes up and down like this, but all functions are not like that. So there might be functions of this variety, for instance, which do everything, okay. So then there will be issues at some points. So if you give me slope, there will be multiple points which will have the same slope. So we have to pick a branch or whatever. So what I'm saying, but whatever I'm saying, the following will be true. Locally in the neighborhood of these three extrema, that g of p will have some behavior. There will be there might even be invertibility issues. So, but that these three extreme, so we may not know what f is. We might, what I'm saying is f of x. So looking at this, g of p will have two minima and one maximum. Okay, so
Sir, is it true for even negative x?
oh yeah. I mean, there's nothing special about x being positive or negative. Yeah, slope can also be positive and negative, right? Yeah, I just drew. I mean, so I can move this axis if you want. Okay, so the key point is Legendre transform preserve extreme. Okay, and now let's go back to the Euler-Lagrange equations story. Euler-Lagrange equations are extremizing some action, right? Okay, so the Hamiltonian which you get from that, so it's just the same statement out here which I already made before doing this thing, is that Hamilton's equations are extrema for something else, and these are extrema for the action. So in some sense, so the Legendre transformation is quite nice in that sense. It preserves this property. So what it says is that Hamilton's equations of motion are equivalent to, not same as, but equivalent to the Lagrangian equation formulation. So that is the punchline. And I will share a nice, there's a nice American journal. That I'll share on Moodle, okay? And it's worth reading. Okay, so it gives, I mean, they do a better job than I did, but the general ideas that I've given will go through. Okay, so applications of Legendre transform. One we have already seen. We go from Lagrangian to Hamiltonian. Okay. So one more thing which I want to emphasize is that it's if you do it 2 times, you go back to the original function. So where is this definition? Yeah. So we can write this, or we can write f of x equal to xp minus t of t. Right? I just took xp to the, I took f, I exchanged the roles, exchange these 2 guys, and you get this equation. So you can see that if you do it 2 times, okay, so that's what is happening. So see, the point here is that you have the value of the function and the slope of the function, and these 2 data is roughly being carried through.
Okay. Sir, here x is dou g by dou p.
Exactly. So you have to do a different, yeah, absolutely. So x is the slope of, obviously, yes. So x, the independent variable, is dg by dp. Oops. Thank you. Okay. It's the same story, right? X is, we're doing inverse. So now you're given g, and the slope of that is x. Nice. The second application, which is again something, is in thermodynamics, for instance. Okay, in thermodynamics, there are plethora of, what are called state functions. So, for instance, if you have a gas of, ideal gas of particles, or any gas, it doesn't matter, it will be ideal. So, for instance, the state of the system there is given by giving internal energy, volume, and number of particles. And this is something called the entropy. Okay, and there is a Legendre transform, of course, and it takes you to what's called the Helmholtz free energy, which is F of T, V, and N. Okay, so this is the Helmholtz free energy. Okay, and this is also Legendre transform, but there's a subtlety. I mean, so So what is happening is that your U is getting traded for T, but I think the correct statement it's like 1 by T or KBT or whatever. Okay, 1 by T. Okay, is a correct variable. Okay, so it doesn't matter, but the convention is to write it here. But in thermodynamics, these have meanings. So ask which state function should I use? It depends on the experiment you're doing. Suppose you're doing an experiment where the control parameters are temperature, volume, and number of particles. You're fixing all these things and controlling temperature, then the Helmholtz free energy is the correct guy. But if you're not controlling temperature, but you're doing something to keep the system at, fixed internal energy U, then the entropy would be this thing. Okay, so similarly, you could do Legendre transform with respect to V, and the canonically conjugate variable is P in this case. And for V, for this, it is, I guess, mu, the chemical potential. So you get a plethora of state functions by doing various Legendre transforms. And so also there'll be signs. So entropy, you maximize entropy, and there's a minus sign in the conventional definition of F. So you minimize Helmholtz free energy. Okay, so these are small details which might be very confusing, but these are two beautiful applications of Legendre transformations. Okay, so now we'll go back to. I need to generalize, so I'll pause here. Are there any questions and comments? Okay, there appear to be none. I'm doing a fantastic job. Got to give myself a pat in the back. We did only for 1 degree of freedom. For 2 degree of freedom, I'll do it for many, but I'll stick now to just 2 because I want to illustrate something. So let's say we have 2 degrees of freedom. So we have L as a function of Q1 dot, Q2 dot, Q1, U2, and T. And we do one Legendre transform with respect to, say, P1. We replace Q1 dot with P1 dot, so we get P1 Q1 dot minus L. Okay, and this R will be a function of what? Someone tell me, what are all the independent functions of R?
P1.
P1, yeah. You will put P1. Of course, here also I have not defined what P1 is. So P1 will be dL by dQ1 dot, right? So that's also done. So it will be P1, Q2 dot, Q1, Q2. Then we can do a second. And now we get something which is a function of only P's.
So won't it be minus R?
One second. Let me just write this. Yeah. This is what you are referring to, right? Now it's okay? Thank you.
Yes, sir.
Okay. So when you have 2 variables and you do, so it's very funny. So with this R guy, you're in Lagrangian in one variable and Hamiltonian in the other variable. So you'll have Hamilton's equations for P1, Q1, but you'll have Euler-Lagrange equation for R. This has a name. It's called the Ruthian, and it's used in some problems. Okay. But we can always do, and usually what one does is to go straight away. You don't have to do it in 2 steps. You can do it in 1 step. So we can say that H equals to summation. So now I write for general case. Okay, and what are Hamilton's equations? Okay, so these are Hamilton's equations. And this minus sign is important. Never forget if you write it without that minus sign. Okay, so again, now you can see that this is this is an example of a dynamical system with two n variables. Okay, but it is not generic. Because why is it not generic? You can write many complicated things because the RHS is determined by one function. The Hamiltonian. Okay. So this is not the most arbitrary guy. So remember I told you earlier when we were discussing dynamical systems, things which permit Legendre or Hamiltonian formulation are like, very, very small corner, very, very special. Okay. That's one nice thing about Hamilton's equations. Are perfect for simulating on a computer. So suppose you're given a t equal to 0 and you want to go to say t equal to n, t equal to capital T. Okay, we want to evolve. Okay, what you do is you just break up. You write t to be some capital N, which you can make arbitrary or small with some epsilon. So you can just integrate. So you can just write it like this. So let's do this big vector x, which is just q1 to qn, p1 to pn. Okay, and the equations become dx by dt equal to something which I won't write. We know what that is. But what I'm saying is that x at epsilon will be x at 0 plus epsilon times whatever is on the right hand side, right? So we can integrate, and if epsilon is small, we can throw out epsilon square. So we get this thing. So keep on repeating these things. So x at 2 epsilon will be x at epsilon, but again epsilon times there are these triple dots evaluated at epsilon, of course, etc., etc. Okay, so you can integrate. So this is numerical integration. So this is really cool. Okay, so I'll just conclude my lecture today with observables in Hamiltonian formulation. Yeah, go ahead. Somebody's asking a question? Keep going. Oh, no question. Okay. So what it says is that motion is happening in phase space. Okay, and so you look at some function of arbitrary pi's, qi's, and t, possibly even t. Okay, so by the way, there's a term which people use. So phase space is just a space of p's and q's, and extended phase space includes time. Okay. So it's one dimension higher. So it's 2n plus 1 dimension. So this is 2n plus 1 dimension, and this is, and phase space is 2n dimension. Okay. So this is how we would look at observables. Would be functions like this. Okay. So for instance, if we might want to measure some quantity, let's say we want to measure energy. Okay. Then for the energy, the function is just the Hamiltonian. So that's by convention, because we'll see why that term. So the value, okay, so Hamiltonian H of Pi, Qi, the value is usually called its value at a point in phase space is called energy. Okay. So this is just standard definition. So this, but it's also an example of an observable. Okay. So similarly, we could just say, T of, some P square, or T, some function only of P, something like summation over I, Pi square upon 2n. Okay. For instance, this could be the total kinetic energy or whatever. That's an observable. Okay. So what we will study next time is to ask ourselves, how will this vary? Okay. With time. Okay. If you know the trajectory, we can actually input that, and we can work out, and we'll start seeing some beautiful structure, and the structure that we will see will connect up to quantum mechanics. It's probably the closest you can get to quantum mechanics while doing classical mechanics. Okay, so I'll just stop here. I'm done with today's lecture, and I'll pause for questions.
Sir, are we defining energy in a new way? With the value of H at a point in phase space.
Mm-hmm.
Are we defining energy in a new way here?
Yeah, in some sense. Yeah, but it will agree with your naive this thing. So we will see that Hamiltonian is a generator of time translations in some sense. We'll see that momentum is the generator of translations in space and things like that. So what does it mean to generate something? These words will become big concrete mathematical statements. Okay, so we'll see that in the next lecture. We'll also do some examples. This was very, very formal today. There was really no examples. You can go back and check for the free particle for the part. So, you can even at least check that H for a particle moving in a potential is P square upon 2m plus V of x. Or first and only example we looked at today. Okay. So here you will agree this is what we call energy. Okay. So, but there is a reason for defining these things in this fashion, and it's very clean in the Hamiltonian formula. It's not that I can't do it in the Lagrangian formulation. We can, and we will do it at some point. Okay. Any other thing?
Sir, in Legendre transform, can you repeat the part for fx is not quadratic in x?
Yes. So what I said is, so point was that when it was quadratic, we know it's a minimum or a maximum, right? Suppose it's not. Okay. Suppose there was a more complicated function. So I drew a function with 3 extrema. Right? So
Okay.
what I'm saying is that at least we can do locally, we can do the Legendre transform. There will be global problems. We have to handle it because, giving the slope is not unique, because there can be multiple points with that same slope which occur in several values of x. So we can't do that, but we can do something slightly, we can focus on one neighborhood of one extremum, and there when you expand, which is what I did. So like here, And here we can expand about, say, this minimum, and then it will look like ax square. That's all I must say. So locally you can do this thing, and you will see that this property continues to hold. Okay, so what I've done is not given full proof, but you can at least get some intuition. I think intuition is more important.
Okay, sir. Thanks.
Okay. So locally that it's still true, right? In that neighborhood it will work. That's all I'm saying.